really works. Okay, look, in real life, when you want to make an argument, right? You want to tell someone something, or you want to make someone do something. There's three special words in English language. And I want this, and I want this. Both of them I need. Then I will be happy, right? And both. I need both. Then there's or. I want this or that, right? Either one or even both of them. Then I'll be happy, right? If I want apples or bananas, right? You could give me apples, I'll be happy. You could give me bananas, I'll be happy. You could give me both, I'll be extra happy, but I'll still be happy. Okay, now look. Let's just say happiness, right? Happiness is a 1, right? Happy guy, me being happy is a 1. Oh wait, I should flip this camera because it's inverted. Mirror, actually. Right? So happiness, right? Me being happy is a 1. And me being sad, I never got my banana, I never got my apple. Sadness is a 0. Okay? You know, computers use 1s and 0s. There's 2 states. Happiness, sadness. Or it could be a water pipe, right? With water being in the pipe as a 1. Or water not even being in the pipe as a 0. But computers use electricity. So what is our 1? Our 1 is electricity being in a wire. That's our 1. That's our happiness. And electricity not being in the wire, that's a 0. That's our sadness, okay? Now, I told you and or. There's also another special guy called not, right? I do not want this, right? You could give me anything in the whole universe except that one, right? And then you get that, right? There's and or, and not. And with these 3, you can construct any argument you want, right? Right? You can construct anything. But look, a computer is a physical object. And I told you we could get the idea that based on what I'm saying so far, computers somehow implement and, or, and not, right? Okay, but they're structures, they're physical structures. So let's talk about that, right? Let's talk about it in the analogy of waters. And I'm going to use a different marker because I don't think the purple's showing up good. So let's use this one. Okay, imagine I had a pipe, right? So I have a pipe and I had a little tap, right? So I could come here, turn this tap on, and let's just say water's flowing in, right? And the pipe continues, and I have another tap, right? And then, so what's going to happen? Water's coming in. The only way it could get to the output, this is my output and this is my input. The only way is if we'll call this tap A, and tap B, right? Both taps need to be on, then water will flow through. This is a physical structure, right? You can do the same thing in electronics design. You could search up something called a transistor. I'm not going to go into depth of how they really work, but think of it as a tap, right? And someone could come turn the tap. But the beautiful part in computers is there doesn't need to be someone to turn it. The turn is another tap. So I could feed another pipe in here to turn it. You get that? And if there's electricity being on this tap, it would turn it on. And if there's no electricity, it would turn it off. You see how you could chain them together? Okay, cool. Now, this is and, right? And why? Well, let's draw something called a truth table. So we'll call the output X. So, what are all the combinations of taps I could have? I could have both taps are off, right? That's one combo. So let's just say 0, 0. 0 being that the tap is off. So both taps are off. What's the other combo? I could have tap A off, tap A on. So 0, 1. So let's say 1 is the tap on. Then what's the other combo? Well, I could have this one off and this one on. So that's the other combo. And the final combo is they're both on, right? Now, based on our logic of how water flows, we could tell that if both taps are off, well, we're gonna 0, right? If one of them are on, it's still nothing. Both of them need to be open, right? This is called a logic gate. And your computers will have billions of these. There's other ones, but we went over the first one. This is called an AND gate. Literally and. A and B need to be on, then we get water going through. Perfecto. Okay. So yeah, you can make a circuit that does this. Search up transistor. But in modern processors, they use something. It is but they use MOS, CMOS. But I don't know truly. And there's lots of different types of transistors. Lots of different types of designing them. Crazy things. But, okay, what if I had this structure now? Pretend I had this structure. I had a Y, but I had a tap here, and a tap here. And these both connect like this. And we just have water. There's just water like this. So they both fall into up to the taps, right? Now, what does this, and these are taps. It's not a smiley face, it's not it's not like a, what does this look like? Squidward? Yeah, it's not Squidward, but anyway, so I'm getting okay, what are the combinations? Remember, we have the different combinations, and think about this in logic. How would you get, and this is our X, right? How would you get water to flow through the bottom? Well, this is pretty trivial. If you ask me, well, okay, these are the combos. Both of them could be off, one of them could be on, the other one could be on, or both could be on. And there's a little glare there. So I'm just gonna move you. No, let me get rid of the glare. Because that would be kind of annoying. Okay, there, perfect. Right, so look, both of them are off, 0. At least one, we have a flow, right? Whoa, we get water. 1. This one off, I turn this one off, no water anymore. But I turn this one on, right? I turn that one on, that one off. I have 1. I turn them both on, I still get flow. So look, this is an OR gate, right? This is OR. Remember, before we went over AND, right? Where it's just a line of taps. And we have OR, which is just a U, right? It's a U shape. And I could keep adding more taps in here, and you can make a big OR gate with a bunch of ORs. Even with the AND gate, if you just chain a bunch of taps together, you can make a 3 input, 4 input, 5 input, 6 input, 7 input, 8 input, right? And well, yeah, we'll talk about bits after. We just need to pin down the gates first. Okay. And there's one more called the NOT gate. So I don't know how to really draw this one because it's kind of magic, because you just have a pipe, and we'll just draw the NOT gate as this. This is the actual symbol. But basically what this guy does is if I have water flowing in, it doesn't give me water out. It's not. It flips. It literally negates. So pretend I had no water. Try to guess. If I had no water, what would you guess would be on the output, right? The opposite of no water. What's the opposite of no water? There is water. So there would be, magically out of nowhere, there'd be water coming out. But truly what's actually happening is this chip has a ground and a positive, and it's just, the tap is just getting generated from here. There's some circuitry that just allows it to come from there. Okay, but anyways, so look, we have AND, OR, and NOT. And we could derive other gates out of these. And I'll just quickly go over them. And we'll actually start using the true symbols that computer designers use. So remember I had AND, right? The double tap guy. The double tap guy. So this actual symbol is a piece of toast. So it looks like a piece of toast. You have an input, 2 inputs, and the output, right? These are my taps that are activated by switching, turning them on. But we're dealing with electronics. So the switching on is just feeding electricity in. That's the switch on. We're feeding electricity in. This is AND. So this input and this input, then we get an output. Okay, then OR is, kind of looks like a, I don't know, what does this look like? When you're, if you've ever been to swimming class and they have those little paddles, I don't know, it kind of looks like that. So this one's OR, same thing. 2 inputs. And then NOT, we know that we have this one. Okay, but let's derive the 2 other ones. What would happen if I take the AND gate? Okay, let's take the AND gate. Let's take the AND, put an inverter, and feed it like that. Well, okay, let's just draw the truth table. And let's figure out what is really happening here. Look, what are the combos that we have? We could have both of them off, the B on, A on, or both of them on. And at this point, we'll call it X, and at this point, we'll call it Y. So I'm going to make another column for Y. And we know that we already know this one. We already learned this one, right? 0, 0, 0, 1. is because A and B, then we get the 1. And this one just flips it, so I don't need to think about anything. I could just go 1, 1, 1, 0. Now let's erase this, because we don't care, and we don't care about this. And truly, how they are actually drawn to simplify the design is actually, you put a circle just represent NOT. So now we have the NAND gate. Now, there's something called De Morgan's theorem, which is extremely important, and I will tell you De Morgan's theorem, but we have to learn a little bit more before then. Just a little. Actually, no, we don't. Because look, look at this. 1, 1, 1, 0. 1, 1, 1, 0. How can we say this in English language? Look, both of them off 1. Well, either one. I see OR logic. Do you know why I see OR logic? A or B can be a 0. Look, A or B can be 0. Then we get a 1. So I'm going to relate the NAND gate to the OR gate right now. So I'm going to draw OR gate. But look, the OR gate, that's looking for zeros. What does that really mean? We're taking the inputs and flipping them. Taking the inputs and flipping them. These are equivalent. Equivalent. And you could also draw it like this in short form, where you just put circles. These are all equivalent. So this is the first part of De Morgan's theorem, where if you have a NAND gate, think about a NAND gate as an OR gate looking for zeros. That's really what a NAND gate is, right? I used to, this is a problem I used to have where I'm like, oh, I can't remember the truth table. I used to get mixed up. But just think of it as an OR gate that looks for zeros. That's it. Okay, then we could do the reverse now. So there's another side of De Morgan's theorem. And let's do it right now. So let's take our OR gate and let's feed it through an inverter. And you could try to infer what is going to happen. It's kind of a similar pattern. We'll call this point X. We'll call this point Y. And we have input A and B. Let's do it the same thing. A, B, X, and Y. So we have the combinations of our inputs, right? And we know this one. We already went through the point X. We already did this. So we know it's OR. A or B have a 1. But look, now we feed it through the inverter. So we just take these and flip them. 1, 0, 0, 0. Do you see AND logic? Do you see AND logic? Forget X. We don't care about X anymore. What we're really looking for is something called a NOR gate. This is called NOR. Right? That's like an English word too, NOR. So do you see AND logic? Why do I see AND logic? Because A and B need to be a 0. A and B need to be a 0. Then it's a 1. So let me try to relate this one. So I'm going to draw an AND gate. But an AND gate that looks for zeros. And how do I make an AND gate look for zeros? I flip the inputs. I flip the inputs. Because then it'll only turn on when both of them are... Because look, if I feed zeros in here, then I flip them 1, 1. AND gate only turns on with a 1, 1. So this is De Morgan's theorem. And I just want to summarize De Morgan's theorem quickly. Right? And then I'll show you 2 more gates. And then, yeah. So look, remember we did this one, the NAND gate, equivalent to an OR gate with flipped inputs. Same thing, nothing different. Okay, now we related the OR gate, the NOR gate. That's equivalent to an AND gate with inverted inputs. Now, we just learned De Morgan's theorem beautifully. Now, there's also 2 more gates. And you can construct this gate out of whatever I told you. You could, but we won't go into too much depth of this. But there's another one, and this is my favorite symbol because it just looks cool. It's basically an OR gate, right? It has the same symbol as an OR gate, so it's gonna have some sort of OR logic just off the bat, just based off the symbol. But we have an extra fin. This one is called XOR. Right? It's also sometimes EXOR. And what the EX and the X stand for is exclusive. Exclusive. You could try to infer in English language what that would really mean, but I'll just draw the truth table for you. And you can actually create these out of I forget exactly, but you could create any gate out of NANDs and NORs, by the way. So NANDs are universal gates, and NORs are universal. So you could construct all gates out of NANDs only. You could search it up. I don't remember them off the top of my head, but okay, look, I'll tell you this one. Try to guess what exclusive OR, because look, I'm just gonna draw what an OR gate is first. An OR gate would be like this. But exclusive. So this one, we're only doing exclusiveness. So this is what the XOR gate really does. But in English language, if they're different, have a 1. If they're the same, give a 0. And then you could guess. We could have the circle version of it, and all we do is put an N here and an N here, XNOR, and you could guess. Go here, and just flip the bits to a 1, a 0, a 0, and a 1. And I just showed you what computers are. This is what computers are constructed out of. Billions of AND, ORs, NOTs, XORs, XNORs, NOTs. You combine them. And there's also one more I should talk about. It's called the buffer and the tri-state buffer. And I might as well say it because we've been this far. But before I should even go into that, we should learn binary because it will make more sense. We should learn binary and how numbers are actually represented. Now look. Electricity only conducts on wires. So imagine I had 4 wires. It's called a bus. This is a 4-bit bus. And the way computers actually represent numbers in the processor is using buses. So this is like your first digit. You know, in regular numbers, we could have 3049, right? So I could put the 3 here, the 0 here, the 4. So each wire carries 1 digit, but we're dealing with binary, right? It's a wire. It could have electricity or no electricity. So we could have binary numbers on here. We could have a 1001 on this set of wires, and the 1001 would be transferred through the wires all the way here. You can move information around. Okay, cool. But now let's learn how numbers are actually represented, and we have to rethink the way we actually think about numbers, right? We have to rethink the way we think about numbers, and I'll show you. And it's very elegant. Okay, so let's just start off with regular. Let's say we had the number 350, right? What does this mean? Well, we have the hundreds, the tens, and the ones. Okay, let's keep this as, let's put a value in here, 7, right? So what is this? 3 times 100, right? Plus 5 times 10, right? We learned this in like grade 4 or whatever. And then we have 7 times 1, right? We learned this. And we just take the 3 from here, we take the 5 from here, take the 7 from here, and we multiply it by the place values. We know this, we already know this. Okay, this is just gonna lead into how we can use different number systems. And I need a paper towel to, I don't know where I threw it. Oh, here. Okay. Now look. Let me say one thing. So we had 10 to the 0, which is the ones place. We had 10 to the 1, which is the tens place. 10 to the 2, which is the hundreds place. And you could keep going, right? And why do we have 10? Because we have 10 symbols. We have all the way up to 9, right? 10 symbols, 9, 10. But we have a different number system. We only have 2 symbols. So what are we gonna do? Right? I only have a 0 and a 1. So what's the pattern for these? Well, we have 2 symbols, so I'm gonna do 2 to the 0 this time, right? That's 1. Then I'm gonna do 2 to the 1 this time. That's 2. Then I'm gonna do 2 to the 3. 2 to the 2 this time, that's 4. You ever play the game 2048? You know, that game where you're doing the tiles? These are the same numbers. 2 to the 3, 8, 16, 32, 64, 128, 256, 512. And this is part of the reason, well, it's not exactly the exact values, but your phones come in 4 gigabytes, 32 gigs, 64 gigs. It's not exactly 64 gigabytes, but they just round it just to like make people happy with the bases of 2. But you know, 64K, okay, all those numbers is because of these. But now I'll show you beautifully. Pretend I had this binary number. And what you're gonna do, let's break these into columns. And every digit that has a 1, This one has the 1, this one has the 1. And it's the 8th place, and this is the 1's place. So I'm going to do 8 plus 1. This is 9 in binary. 1, 0, 0, 1. Now if I were to do this, well, I have to add this one now. So it's going to be 4 plus 8 plus 1. 13. So 1, 1, 0, 1, 13. It's easier than regular numbers, and I could promise you that. As long as you know how to add 1 and 2 and 4 and 8 and 16 and 32 and 64, and you could see where the 1's are, you ignore the 0. You ignore the 0. Right? Because we're just doing 1. What we're actually doing here is we're taking the 1, the actual value, multiplied by 8. And then we're adding 1 multiplied by 4. And then we're going to do 0 multiplied by 2, which is always 0, so forget that. You see the pattern? This is beautiful. So we've just learned binary easily. And I might as well just teach you hexadecimal because it wouldn't take 2 minutes. Like, I'll just teach you hex very quickly. Hexadecimal, hex. Hex is a hexagon, hex 6. Hexadecimal. Hex is 6, deci 10. 6, 10, 16. Base 16. What if I had 16 symbols? 0, 1, 2, 3, all the way to 9? Oh, I'm out of symbols. I'm going to make the symbols. Let's just use A, B, C, D, E, and F. So this is actually 10. This is actually 11. This is 12. This is 13. This is 14. This is 15. So let's do A, 7, 1. We have 16. What? This is 16 to the 0. 16 to the 1. 16 to the 2. This is just 1. What's 16 to the 1? 16. 16 to the 2? 256. So let's take our A. We know A is actually represented as 10. So I'm going to take 10, multiply it by 256, and that's just 2560. Okay, then I'm going to take 7, multiplied it by 16. I'm not going to do that, but okay, we add that, and then we do 1 times 1. So that you see that. And you can do any, what if I had base 64? What if I had base 69? What if I had base 2951? I need that many symbols. You just do the power and you can make, this is how you rethink numbers. We just rethink the way how we think about numbers. Oh my god. And let me just show you for the fact, just a cool like little side fact. Is like if you go on YouTube, okay? I'm gonna go on YouTube right now. I'm gonna just press this random video. And okay. You see that code in the top? Oh, it's like XISG49. That YouTube uses base 64 to encode their videos. So every video is given, the base 64. That's why we have uppercase and lower cases all the way to X. There's so many different symbols, right? Because it's base 64. And the higher your base is, the more you can encode per symbol. I mean, per digit, because you have more symbols to represent per digit. Then there's just more combinations you could have. You get that, right? And our numbers, our regular numbers, we only have 10 symbols, 0 through 9, right? And it works pretty well. We have 10 fingers, yeah? It's pretty good. But yeah, but now, okay, and then you could, okay, I'll just show you how to convert from binary to hex, which is very beautifully easy. What you're gonna do, we have to know a few facts first. This is in regular number, base 10, like this side will be our regular human number, this will be binary. So this is 0, this is 1, this is 2. I'm going to stop putting equal signs. This is 3. Why this is 3? Because it's 2 plus 1, 3. And this is 4, the next power of 2. Then if I add 1, if I put 1 here, see 5, I just added a 1. 6 is just 4 and 2. So you get the pattern, right? But I'm gonna draw them all out because we want to learn something. See 8. See, notice these. The juicy numbers always have only 1, right? The 8s and the 16s and the 32s and the 64s, they only have 1 somewhere. Why? Because they're in the place value that they need to be. But okay, let's keep going. Let's go all the way up to 15, because we need to know these facts in order to convert from hex to the binary and binary to hex. So okay, we got up to 9. Then 8 plus 2 is 10. And then but I'm actually gonna represent that as A. Remember we learned hex, so we're just gonna say A. Then I'm gonna do 1 0 1 1. This is 8 plus 2 plus 1. 11, 12. Why is this 12? Because 8 plus 4. 13, I'm just going to add a 1 in the end, 13. 14, you get this, right? I hope this makes, and all F. Remember, this was 15. And look, if I were to go to 16, 1, 0, 0, 0, 0, the next juicy boy. So that's 16, but we only have, okay, but anyways, look, we need to remember these in order to convert quickly. If you want to convert quickly, you have to remember these. And over time, it'll just be, oh, and I lost my nappy can again. Oh, it's right here. Okay, but over time, the more you use it, practice, you could just know these off the top of your head. Okay, I'm gonna take a random binary number, and I'm just gonna straight up convert it into hex. Let's just do a big boy. 1 0 0 0 1 1 1 0 1 0 1 0 0 0 1. And how you convert this into hex? You start from the back, you group them in 4s, right? So that's 1. Because the pattern that I just erased, you have to remember them. So that's 1. This one right here, that's 5. This one right here, that's 7. And we're going to add an extra 0 just to make it 4, and that's 4. So in hex, this is 4, 7, 5, 1. And I could convert it back. Well, this is 4, 0, 0, 0, 0, 7, 5, 1. Done. This is it. So I just showed you the beauty of hexadecimal, blah 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 blah, and I kind of feel kind of lazy, so I'm done teaching because I just did a little lesson. But I hope you guys learned something. If you have questions, I'll answer them. Maybe tomorrow we'll go into more depth of registers and different type of structures you could create, right? I just introduced you to the building blocks, right? Now we could actually construct things. Multipliers, adders, shifters, comparators, right? A whole CPU, right? So yeah. Oh my god, thank you guys for the gifties. That's actually very kind. I need to flip my camera around and mirror it because, if you look at my face, and mirror it, it just looks lopsided, right? I don't know, I like it this way. But thank you guys. You gotta teach us okay, tomorrow. I'm kind of feeling a little tired of doing this. But, alright, yeah, you're welcome. I'm gonna read some comments. I wish I was passionate about IT. You can be. But look, is that not beautiful? And think about the complexity. Look, like, we have these laptops, we have these phones, the phone especially, right? And there's billions and billions of little, But, let's see. Thank you, Python syntax, very much. Actually very, and this. I'm sorry for pooping on your name. But thank you guys for those little gifties. So, okay, good. We've learned a lot. What is this material you're teaching? This is called digital logic. So, and if you want to learn more, I really recommend just do this, just do your own research too. So I'll give you some search terms. Digital logic, Boolean algebra, digital design, those 3, and the search in PDF, okay? And maybe go on YouTube too. YouTube, beautiful. Right? And I recommend I showed you the basic gates. Search up adder circuit on Google, and you could see the gates that I told you. And you could try to follow the traces and thing. But, wait, something's weird. Never mind. Make a course? If I had lots of time and extra time. Honestly, I'm kind of lazy. But I feel like this is okay. Thank you for sharing your passion. Very enjoyable to learn from. Thank you. Such a fun subject and course. Yes, Larry. The lobst 3. Oh, how do words to hex? I'm not exactly sure what that exactly means. Maybe you might have a typo. Digital design is actually awesome. It actually is. And okay, maybe I should go back to work. No, but I fixed that. What's my next step? To add the registers and all the buffers. But I'm a little lazy if I were to be completely honest with you. I don't know what I feel like doing right now. I don't feel like explaining anything. Let's just I think I might just go for a bit, eat a little, come back, maybe. I don't know. Please save the live. Yo, it's always saved. It's always saved. The alphabet in hex. I'm not exactly sure what that exactly means, but this has nothing to do with computer science. It kind of does actually, but it's like a sub. Okay, look, there's computer science, then there's software engineering, computer engineering, right? There's the two branches. And computer software, yeah, you kind of, because look, in Java you could do your if statement and you have some and or, right? You could, and the not is the exclamation mark, and the or is that line thing, and the and is the double and, right? So kind of, it's the same type of thing, bro. You're allowing, okay, whatever. But yeah. Where did I leave off? Oh, hi, Akafa. What's up? Can you teach IPv6? I don't know. I don't know too many things of this. Switch to Carlton. But I think I should actually go because I'm a little lazy, to be completely truthful with you. Can you explain bus? Okay, I guess I'll just go over that quickly because it's pretty fundamental in what we were talking about. But where's my eraser? Because I only oh yeah, I didn't even explain the tri-state buffer, and that's what I was supposed to be doing. So let me just do that, and then I'm gonna probably. Okay, look. Remember, I don't know how many people are here from the part where I was talking about the lines. Well, I'll just re-explain it. Okay, no, I can't because I'm just gonna go off into a tangent. So remember, you can have the 1, 0, 0, 1, and it gets transferred all the way down here. Why? Because there's just conductors, and they just could transfer things. But let's say I had a component here. Let's just say we had a thing, right? And it connects like this. Right? What if I had another thing, like a little piece of circuitry that just puts to the bus, it broadcasts it, right? This is what it sends all its data here. Pretend this guy is actually the source of the 101. It broadcasts it, everywhere could see it, right? But what if I had another device here? But what would happen, look, ask yourself, what if this guy was giving out a 0001? What's going to be on the bus? It's just going to be garbage, corrupted. It's just going to be mixed. It's just going to be absolutely garbage. Only one thing can be on the bus at a time, and this is what a tri-state buffer is. So there's, I wouldn't say they're gates. I don't know the correct term for whatever I'm trying to say here, but we need a way to disconnect something whenever we feel like it, and then reconnect it whenever we feel like it, right? We need a piece of a circuit, a something that could somehow disconnect from the bus. Then this guy just disconnected, and this guy could talk. This is what a tri-state buffer is. So I'll just show you the symbol. It looks kind of like this. It looks like an inverter. Remember, the inverter had the circle. This one, you take out the circle, is just... So you could guess. This is the same thing as just a wire. Right? Because there's no circle, it's just a buffer. These are actually used to amplify a signal. So if I have one coming in here, but maybe it came over, like it's just pretty weak, or it's some high impedance, like you want to do... Okay, let's not even talk about that. But let's say it's a pretty weak one. Then I want to boost it again, then it'll become strong again through the buffer. But I'm not going to go into the details of the analog things, but what would happen if the symbol actually looked like this? Now this is a tri-state buffer. And this is the device. What if I got 4 of them together? Right? I got 4 of them together. And I connect all the control. I connect all these together. And this control signal it acts as a disconnect. If it's a 0, it's like they're all cut off on this signal. Right? And then I could feed my data in. And if this is a 1, then it's like they're all connected back again. Right? They're all sharing the same control signal. And your modern processor is 64-bit, right? 32-bit processors, maybe 128-bit. There would be 64 of these down. Right? Your modern processor is 64 bits. This is only 4 bits I've drawn. And the computer I'm making here is a 16-bit, right? 16-bit processor. So yeah, okay, there. I have nothing else to really say. And yeah. I think I should go. Okay. We will talk again.